Okay, good morning, everyone. Today, I'll wrap up the topic of AC power. We have a couple of slides remaining. So we'll go over the concepts and the equations, the mathematical equations, and then we'll look at example one. Example one. My annotations are already on there, okay, in the interest of saving time. So students do not have to take notes. What I would rather want students to do is to actually follow along the explanation as follow along as I give the explanation. That's for example one. Example two is also about AC power, but it will not be included for the final. Okay, so I would suggest students review example two because again, every step is outlined in detail. So even if you just read through it, it should make sense. And then if you have questions, reach out to me, but it will not be part of the final. I will not ask students a similar question in the final. Okay. All right, so let's take a look. Let's go to the class notebook. And yes. No, AC power is going to be on the final. I said example 2 of AC power will not be on the final. So I'll show you. Let's see. So section 4. This is example 2. This will not be on the final. Or more accurately, more correctly, it said this type of problem would not be on the final. Okay. This type of problem will be, which is straightforward about finding power for an AC component. Yes. No, we will have power triangles, but I will not ask students to reverse solve it. Yes. Filters are not. Filters we already assessed in the quiz, on the long quiz on Monday, and that's it. So final exam page does not include chapter 6. We just did like a 25-minute assessment, and I think that's sufficient this close to the final exam. Okay, so let's look at the last remaining slide for the equations. Before that, let's think back to chapters 1 and 2. Okay, when we think back to chapters 1 and 2, actually chapter 1, we talked about power. Like power for electric circuit is simply the product of the voltage and current, V times I, right? In chapter 3, when we looked at inductors and capacitors, we still use those equations to derive the power for the inductor and the capacitor. And we'll still use the same because that fundamental relationship does not change. Electrical power is the product of the voltage and current. So for a resistor, if you were given the value of the resistor itself, we can find the voltage and the current for the resistor, VR and IR. We take the product VR times IR, that would give us the power for that resistor. Okay, and again, I'm talking about chapter 1. PR, power for a resistor, can be given by the product of the resistor voltage and the resistor current, VR times IR. So if you were given the voltage for a resistor, you could find the current using Ohm's law and then apply this equation. Or if you are given the current for a resistor, you apply Ohm's law, find the voltage, and then still apply this equation. That would be an extra step. But combining this equation with Ohm's law, you can also find PR as V squared times R, or, V squared over R or it would be I squared times R. Does everyone remember this? V squared over R or I squared times R. This form is still valid. Okay. When we talk about AC power and we talk about resistor, inductor, and capacitor, you will still apply the exact same equation. No difference. So I'm starting at the bottom of the slide right now. And then I'll move up. If you look Here for a resistor, this is still the same format as I square times R. This is still V square over R. And because we are talking about average power, it is the RMS values of the voltage and the current. So it is V RMS square over R and I RMS square times R for a resistor. The same equations as applied to an inductor and capacitor would simply substitute the resistance with the reactance, X. Okay, so if we wish to find the power for a capacitor or an inductor, that fundamental principle still holds true. Electrical power is the product of the voltage and current, but because we're talking about reactive power now, that reactive power is represented with the complex numbers or complex math. You have to take the phase angles into account. So it is not as simple as simply just finding VL and IL. Okay, QL and QC, reactive power is a little different. We use the RMS values and we can apply the exact same equations. So QL and QC can be determined using these two expressions. They're the exact same form of what we learned in chapter 1. No different. And this applies to both L and C. So X, the reactance, if you're trying to find it for the inductor, it would be XL. If it's for capacitor, it would be XC. Okay, you guys with me so far? Right, so that's the bottom of the page. Same equation, no different. One thing to keep in mind is that the reactance for a inductor and hence the impedance for an inductor mean XL, ZL, and then the reactive power for an inductor, which is QL, are all positive. Right? That vector is pointing straight up. XL, ZL, and QL are all represented with a plus sign. They're all considered positive. Conversely, XC, ZC, and QC, the reactance, impedance, and the reactive power for a capacitor is all pointing down, minus 90. So QC is negative. Or mathematically, we put a minus sign in front of QC. Okay, QL is pointing straight up. So it's positive. QC is pointing straight down, so it's negative. It's an important concept to keep in mind. It comes from the fact that the voltage and current of a capacitor and inductor are out of phase. Inductor, the voltage leads by 90 degrees. Capacitor, the current leads by 90 degrees. And so we'll call on Eli Manning to help us out. It's not really named after Eli Manning. L is the inductor, C is the capacitor, E stands for electromotive force. And I think I mentioned this in chapter 5 also, if anyone remembers. And I, of course, stands for current. So this mnemonic simply tells you that for an inductor, the voltage comes before the current, meaning the voltage leads the current by 90 degrees. For a capacitor, it's the exact opposite. So voltage leads current, or you could say current lags the voltage. For a capacitor, it's the exact opposite. Current leads voltage, or voltage lags current. In both cases, the difference is 90 degrees. When you try to find the impedance, impedance is V over I, Ohm's law. So V divided by I, meaning the phase angles get subtracted, theta V minus theta I. Again, this is from chapter 5. This is not new. Theta V minus theta I gives you the angle of the impedance. So for an inductor, the impedance is always, always, always plus 90. For a capacitor, it's always, always, always minus 90. That's where it comes from. Anyway, the way it relates here is that the power or the complex power in a system also is a complex quantity. And so we describe it using complex or complex math. So it has magnitude as well as phase. Total complex power is noted by S. So it's magnitude of S and phase. Yes. Yes. In real life, all power is just power. It's not negative or positive anyway. But even mathematically speaking, real power is always positive. And the question being asked was referred to real power. And in this sense, real power refers to the resistive power, P. So P is described as real power. Q is described as reactive power. But make no mistake, reactive power is also real in real life. It can get confusing. We say reactive power is imaginary. We say reactance is imaginary. We say impedance is imaginary for a inductor and capacitor. But they have a physical basis in real life. The imaginary word is describing the mathematical representation of the reactance. Again, this is a common point of confusion for not just non-majors, even EE major students, when they first hear about this concept, it's confusing. Okay, when we say imaginary, it is the mathematical representation of the impedance. It's a mathematical representation of the reactance. Okay, it's represented using the imaginary number, but it is not imaginary. It's not a concept dreamed up by engineers and scientists. Okay, it has a physical basis in real life. When power is sent by a utility company, they're just sending power. That's it. They're just sending power. They're just sending S. Mathematically, we say it's S, but what they're sending is just power. A portion of that power will be used to set up the magnetic field. And hence that portion is reactive power. And the other portion of the power that is used or converted into mechanical energy, we say that is the real power. But all power is real. Take 10 seconds, think over it. Let me know if you have any questions. Yes. Reactance. So L and Z. ZL is J XL. ZC is 1 over J XC. Reactance. So XL is omega L. So ZL is J omega L. And XC is 1 over omega C. So what was I saying? Okay, total complex power, yes. Yeah, that's the reactance. It is basically 2 pi FL or omega L. Okay. That is the opposition. So if we go back to the beginning of chapter 5, it's basically opposition to any change in the input voltage or the input current. Okay, it's the opposition. Yes, that opposition comes from the magnetic field and the electric field. So it's not direct opposition like resistance. So you have incoming voltage or incoming current, sets up the magnetic field. That magnetic field then opposes any change in the incoming current. Yes. Yes. Yep. 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 We do actually measure it. We use the impedance bridge to measure the values of the inductor and the capacitor. And so that impedance bridge measures the value of the inductor capacitor and gives you the quality factor, which measures the reactance of the, actually it just performs a calculation in the inside the bridge or inside the meter. Okay. So total complex power, complex number, it's a complex quantity. So you can plot a triangle, which we saw in the previous slide. You have the real power P on the x-axis, you have the reactive power Q on the imaginary axis. If you join the 2 points together with the hypotenuse of the triangle, you get the magnitude of the complex power. So magnitude of the complex power is given by the product of the RMS values of the voltage and current. VRMS times IRMS. Okay, so magnitude of S is VRMS times IRMS. And the angle, of course, is the power angle theta. That power angle theta is the difference in the phase angles of the voltage and the current. Okay, that's the power angle. Phase difference of the voltage and the current. So from those relationships, we can have a couple more. Equations. It's simply from the right angle triangle trigonometric identities, right? Magnitude of S times cosine of theta and magnitude of S times sine theta. There's nothing new in there mathematically speaking. Okay. Yes.
So the 5 VRMS is divided by root 2.
Yes. We will look.
Could you explain conceptually why?
And we will see that in the next conception. I can explain that after class. I'm going to. So those are that equations, and then the term for the magnitude of S is known as the apparent power. That value is important for the engineers or the technicians who work on the actual electrical lines, because that's the voltage that they would be seeing. Okay, and so magnitude of S is known as apparent power. Units for apparent power is basically the same as S, which is volt ampere, VA. Now, talked about voltage and current leading and lagging for inductor and capacitor. We come to a new term known as power factor. Power factor basically describes whether the load is inductive or capacitive. Okay, it describes the relationship of the current with the voltage. If the current leads the voltage, then we say power factor is leading. Okay, power factor describes the relationship of the current with respect to the voltage. If current leads, then power factor is leading. If current lags, then power factor is lagging. For a resistor, power factor is neither leading nor lagging, because for a resistor, the voltage and current are always in phase. So the power angle is 0. For a resistor, power angle is 0. So power factor is neither leading nor lagging. For an inductor, the current is lagging. Remember, voltage leads the current for an inductor. So current is lagging. If current is lagging, for an inductor, we say power factor is lagging. For a capacitor, power factor is leading. And mathematically, it is described the cosine of theta. Yes. No. Depends on the component and depends on the circuit. If you plot, are you referring to lab 6? It was a series circuit in lab 6, and all components shared the same current. So the source, the resistor, the inductor, capacitor, all of them shared the same current. So in order to apply KVL, that phasor diagram was the summation, the KVL of all the 4 voltages. And you could apply KVL to that loop because it was a series circuit and they shared the exact same current. So in order to draw that phasor diagram, we plotted that current with a phase angle of 0. But we don't actually know what that phase angle was in real life. Does that make sense? Okay, so we didn't know. So current can have any. So as we will see in the next example, you'll see the current actually has a phase. Depends on the circuit, depends on how it's constructed, depends on how the components are connected together. So what was I saying? Okay, yeah, cosine of theta. So it's expressed as a percentage. The highest value that power factor can have is, of course, cos of 0, which is 1, and described as a percentage, it is 100%. For all other loads, inductive, it'll be less than 100%. It'll be like 0.99, 0.95, 0.85, 0.4, 0.6, could be any value. It'd be a percentage. So it'd be like 40%, 50%, 60%, 75%. In real life, utility companies will not supply electricity to a consumer or an industrial consumer unless their power factor is above a certain percentage, meaning it should not be inductive load. Again, remember I said power is sent all at once by the utility company. A certain portion of that power is utilized by the reactants. The rest of it is converted into mechanical energy. So the portion that is utilized as the reactants needs to be smaller, because if that's very high, the utility company does not have the infrastructure to send all of that power all at once. The goal is to make that QL as small as possible. And the factor and the term that describes that is the power factor. So as an example, let's say PG&E had a limit of like 85%, 0.85. And a consumer, industrial consumer, power factor was like 60%. So PG&E would tell that consumer, hey, you need to bring your power factor up above 85%. Right now it's sitting at 60% and we cannot supply electricity to you. So they need to put more capacitors in front of their inductive loads to balance out that requirement of power. And the calculation, analysis, and installation of the capacitor in front of the inductive load is known as power factor correction, which is what students would have done in lab 8. Okay, that's power factor correction. Let's look at, any questions before I go to the example? Okay, so that was saying example 2 is not something that I would ask on final, but again, students should review it. I have step-by-step annotations on there. Okay, it explains in detail how a student would solve or how an engineer would solve a problem like this. So it will help you, it will aid you in your understanding of AC power. Okay, but I'm just letting students know I will not ask a similar question in the exam. All right, example 1. And for this, again, the reason I put my annotated slides on here is so that students can follow along as I explain. So you can take notes about the explanation, but do not spend time trying to write everything down. Okay, the whole point of putting this on here, because this is a long explanation. So I want to get started on that. All right, so the example here is a RLC circuit, and you're simply asked to find power for every component. As engineers, you should extract as much information as you can from the given problem statement. Always. Electrical engineering, it makes even more sense because you have circuit diagrams associated with almost every problem. So the circuit diagram here has all of the information. You have the values for R, L, and C. You have the value for the voltage source, Vs of t. And lest you forget, this also has meaning. Think back to chapters 1 and 2. Which direction is that current flowing? I thought, well, at least I can pat myself on the back about that. For a source supplies energy, so current always goes from minus to plus. It's going from minus to plus. We label that current as I. Makes a turn, goes to the inductor. The inductor current IL is the exact same as the source current or the total current being supplied, which is I. Point of entry is, maybe I patted myself on the back too soon. It's positive. And then point of exit is negative. And then it goes here and splits in two. And we can call that as IR and IC. And again, point of entry is positive, point of exit is negative. And that's how we can find the current and the polarity for every single component. Yes. I mean, current direction, sorry, not the current value. Yes. Yes, steady state. So the AC analysis power, then it's only steady state analysis. We are not doing any transient analysis for AC voltages. So if you see a time varying source, that's an excellent question, actually. It's an excellent question. So the question being asked is, should we assume steady state? And the answer is yes. So for chapter 5 and for chapter 6 and for AC power, chapter 6 is not part of the final, of course. We are always referring to AC steady state analysis, not AC transient analysis. Okay. We have not looked at transient analysis in chapter 5. It's always AC steady state analysis. So if you're in the exam, if you encounter a problem like this, and the voltage is given as a function of time, and I ask you to find the voltage or current in any part of the circuit, is asking for AC steady state analysis. Okay, so as I was saying, we are given the voltage Vs of t, we are given the values of the components. We will represent every single quantity with its equivalent impedance, and also represent the voltage source as a phasor, and then we would solve the problem. Okay, so in this case, it's a 2-in-1 problem. We are asked to find the power for every component. In order to find the power, we need either the voltage or the current, right? V square over R or I square times R. We need either the voltage or the current to find the power for every component. Make sense, right? So the analysis portion is exactly the same as we did in chapters 1 and 2. I will go through step by step and show you the analysis. We'll find the power and current, and that is chapter 5. And then we'll move on to AC power. So as a first step, always draw the equivalent impedance diagram. We see 3 impedances, R, ZL, and ZC, right? Think back to chapter 2, series parallel equivalent analysis. You take a large network of resistors, reduce it down to one single resistance, and that is what we are doing here. We have 3 impedances, 2 of them are in parallel. We combine those 2 together, so we get R and ZC together as ZRC. It is the parallel combination of R and ZC. Make sense? Right? And then ZL and ZRC are in series. So ZEQ, the total equivalent impedance as seen by the source, is ZL plus ZRC. And that's it. That's the end of your analysis. That's the end of the analysis. From this point on, all you're doing is mathematical calculation. This is the end of the analysis. You're taking a large network of resistors or impedances, you're reducing it down to one single impedance. Now you apply Ohm's law and you perform the math. Does that make sense to everyone? Right? Okay, so the math requires that we find the values for ZL, ZC, and then ZEQ. ZL and ZC is given by j omega L and 1 over j omega C, meaning we need the values for omega, right? And at the same time, we'll represent the voltage source as a phasor. To do that, I need the expression to be in cosine form, meaning sine x is equal to cos of x minus 90. So I get Vs of t as 10 cos 100t minus 90 degrees. Equate this to V of t as Vm cos omega t plus or minus theta. Vm is 10. Omega is 1000. And theta is minus 90 degrees. I can write the phasor for Vs directly with a magnitude of 10 with an angle of minus 90. This is still in peak value, right? Vm is the peak value. It is not the RMS value. Vm is the peak value. So keep that in mind. When we go to find power, we'll take this peak value of 10, which comes from the source. The source has a magnitude or peak value of 10. Phasor has a magnitude of 10. But when I go to find the power, I need the RMS value, meaning I divide it by √2. That'll come in the next few steps. Okay. So that was for the phasor Vs. Now you'll find ZL and ZC. And because I do not have a programmable calculator, I simply find both the rectangular coordinates as well as the polar coordinates. So plug in the values into the standard expressions. And I find value for ZL and ZC as 100, the phase angles of plus 90 and minus 90. Once I have ZL and ZC, I can find ZRC and then ZEQ. ZRC is the parallel combination of R and ZC. Plug the values in. If you have a programmable calculator, you can go directly from this step to the final answer, either in polar coordinates or in rectangular coordinates. But you better practice and be confident in your skills and your abilities to program these equations, right? Otherwise, you do what I do and take it step by step. Because I'm performing a division, I'm going to convert the denominator into polar coordinates, divide the magnitudes, subtract the phase angles, and obtain my answer. Let's take a 10-second pause. You think over that. Let me know if you have any questions. Yes.
So we have we have
Voltage does not give ZEQ. ZEQ is just ZL. Yes. Oh, you're talking about omega, the value of omega. Yes, absolutely. From the source. Without knowing the frequency, we could not calculate the impedance. There's no way we could calculate impedance. Because that's omega or F is the function, impedance is a function of frequency. So we need to know that value. Yes. Yes, that is correct.
And then you add them.
No, the magnitudes are simply multiplied or divided. Yeah. Yes. Because it's not DC. It's constantly changing. For DC, it would be open circuit. But in this case, it's constantly charging, discharging, charging, discharging, charging, discharging. So there's electrons always flowing in both ends of the capacitor, right? Always going in one direction or the other direction. So the faster it changes, the faster the rate of flow of charge, and hence the higher the frequency of AC, the closer it behaves to a short circuit. And the slower it moves, the slower the rate of flow of charge. Rate of flow of charge is, of course, current. So if the current is slower, then it behaves closer to an open circuit, which is for DC. Let's see. Oh, and then ZEQ, 50 plus J50. Translate that into polar coordinates. You get a magnitude of 70.71 with a phase angle of 45. So once I have that, what I can do is I can use either the current or I can use the voltage to find the power for every component. In this case, I also want to find the power for the source. So the first step is to find the total current being supplied by that source. On a separate note, the circuit has a voltage source, but it could just as well have a current source. Instead of V of t, they could give us I of t. Your approach should not change. Is that clear to everyone? Right? Yes. It's not RMS. It's still the phasor. We are still in phasor form. We are not yet to the power. Power is average power, and then average power requires RMS values. I mean, which one? This one? RMS is just peak value divided by √2. And we will see that when we apply it to the power equation, which is like the next two slides. I mean, the next two steps. So was I. Oh, so total current I has a magnitude of 0.1414 and a phase angle of minus 135. So the angle is not 0. So Alan, going back to your earlier question, is minus 135. It's not 0. The total current being supplied by the source has a very big angle. Minus simply means it's instead of moving counterclockwise, it's moving clockwise. Okay, minus 135. So at this point, you can, if you wish, apply current division and find the total current. I mean, not total current, the current flowing in the resistor and the capacitor. But, you know, current division in complex math, I don't think many students would want to attempt that. So we'll find the voltage, VRC. But if you look carefully, I have applied voltage division to find VRC. Okay. You can, of course, simply find the total current I times ZRC and find VRC, and it should still be the same. So practice this. I've done the harder one in class. I mean, in the solution, you can do the easier one at home. And you should obtain the exact same value. Then I find current IR and current for capacitor, IC. Again, we are still in phasor form. So again, it's a magnitude. They are all vectors. They're all vectors which require the peak values. Okay, this is not RMS, not yet. Once you have the current and the voltage, you can apply either equation you want. And I have both here. Okay, so you practice this. Once you find VL, you can practice this, but on the left side, I'm using V square over R. On the right side, I'm using I square times R. For a inductor, it is V over X. For a capacitor, it is, sorry, for an inductor is V over X or V over XC. And for the current, it's I times X, I times XC. So if you want to find the power from the voltage for every component, use these equations. If you want to use current, use these equations. You get the exact same answer, no difference. This is to show students you can have multiple approaches to the same problem and still arrive at the same answer. As an engineer, it's up to you to decide which approach you wish to take. As a student in the exam, it is up to you which approach you wish to take. There is no right or wrong. There's only more efficient and less efficient. As an engineer, of course, it might make a difference, right? If you work for a company, company would want the most correct solution at the least cost. Companies are like that. They don't like to spend money, right? So as an engineer, it's up to you to pick the most efficient approach. So this is just to show students that you could take either approach and solve the same problem. So either find the voltage and solve it, or you find the current and solve it. Both approaches are still valid and still correct. And then if you add up all of that power, S is equal to P plus JQ. You remember QC is negative. So QL is 1 VAR and QC is minus 0.5, meaning the total power required from the source is not 1.5 VAR. It's 1 minus 0.5, meaning the total power required from the source is only 0.5 VAR. Take 10 seconds and think about it. As referred to your question about steady state analysis, just a separate topic. At some point, when you first flip the switch on, transient analysis would show that the source would have supplied more reactive power, right? The capacitor does need 0.5 VAR. The inductor does need 1 VAR. So when you do transient analysis, at some point in time, before it reached steady state, the source would have supplied a lot more reactive power than just 0.5. But once it reaches steady state, half of this inductive requirement comes from the capacitor. Okay, so inductor requires 1 VAR and the capacitor supplies half of that. So at steady state, the source does not have to supply 1 for the inductor, it only has to supply 0.5. And that is power factor correction. You apply a capacitor across your inductive load to bring down the requirements of your inductive load. Okay. Take your time, think about it, and let me know if you have any questions. Yes. So volt ampere reactive. Yes. I think let's go back to this slide. I want to make sure that yeah. So it's here on the on page number, I think it's like 3 or 4, slide number 3 or 4. Volt ampere reactive, and then S and magnitude of S is volt ampere, just VA. Okay, so, and that's it. That's the end of the problem. Okay, there are 2 more approaches I want to show, which is going to be very useful as concepts and for your ability to solve these kind of problems. But that's the end of the problem. When it says find or determine the power for every component, source is also a component. So you have to find the power for the source also. So you find the power for the resistor, the inductor, capacitor, RLC, you add it all up. That has to be the total energy, total power being supplied by the source. And so that's what we have here. Okay. Did you have a question? Okay. The other approach is to use the equations from the power triangle. Okay, power triangle. For a source, S is equal to P plus JQ. I put a subscript of S just to show that everything in that quantity is related to the source. SS is equal to PS plus J of QS. We find the power angle because we found the total current in the circuit, right, which was minus 135. Remember? Voltage was minus 90, current was minus 135. So voltage is minus 90. And total power we found, total current we found in the circuit was minus 135. So again, the phase angles for the current would depend on the circuit configuration, depends on the components and how they are connected. Okay. So minus 90 minus or minus 135 gives me a power angle of 45 degrees plus 45 degrees. Current lags, meaning overall power factor is going to be negative, right? Cosine of 45 times the magnitude of S, which is this equation, VRMS IRMS times cosine of theta gives me P. VRMS IRMS times sine theta gives me Q. Add up all three of those, and that gives you the total power S from the source. So if the question was, find the total power being supplied by the source, you could stop at the current, right? You could stop directly. You could stop right here and skip directly to that end. You do not have to find anything else. There is an even easier approach, which is a third approach, which is right here. Total power supplied by the source is simply the product of the voltage and current. In this case, it's half VI asterisk. By the way, do you say you call it star or asterisk? Yeah, some students refer to it star. I guess star is easier to pronounce and say than asterisk. But I asterisk refers to the complex conjugate of I. That asterisk is only referring to I. Okay, it's not for V. It's not for V. But that asterisk refers to the complex conjugate of that quantity. So let's put that in perspective right here. And complex conjugate simply means you're flipping it around the real axis. Okay, A plus JB becomes A minus JB and vice versa. And R with the angle of theta becomes R with the angle of minus theta. So the complex conjugate of I is simply 0.1414 with a phase angle of plus 135. We found I as minus 135. Now it is plus 135. Simply perform the math and you get the exact same answer. No different. So 3 different approaches, 3 different sets of equations to find the exact same answers. Okay. And then we come to the power triangle. Power triangle is the real power on the x-axis, imaginary power on the y-axis, and then the total complex power. Total complex power on the hypotenuse. Here, this was simply showing that if this is 0, QL required positive going straight up, and we applied QC. If this was linear, if this was resistor, then it would be a linear summation. Meaning a resistor would require 1 watt, another resistor requires 0.5 watts. So it's 0.5, and it's 1, and then another 0.5 on top of that. So it'd be 1.5. But because QC, capacitor, is the opposite, QC goes down, minus 90, then the summation of QL and QC brings the value or total value down. And so this is my total Q required. And that's basically power factor correction. Okay. All right, questions? Any questions at all? All good. It's a lot to take in. So review the lecture, review the video, review the notations on there. Especially look through example 2. Okay. If you go through example 2, it will help your understanding of this entire topic much better. I will not ask a similar problem in the exam. What I will ask is similar to example 1. Okay. Yeah. Yes. No, there's no separate. It's just basically concepts. If you students can go through mastering, but especially through the quizzes and then the concepts. Yeah. One separate thing. So definitely look at the final exam page on the website. I just wanted to show that the response rate is up to 53%. So every student as of now will get 0.5 points towards their overall grade as extra credit. Okay. And I will send out an email so that, the response rate can go up high. Friday, this is the end of the quarter. Okay. Friday, I'm thinking of just having like open office hours, either in the classroom or Zoom, or maybe both at the same time. I haven't yet decided. But again, no other new information to do. I think we have covered pretty much everything that I wanted to cover by the end of the day. Oh, you mean like approval? It's pretty much all approved. So now, so I'll just send out an email again saying that, even if you fill it out on Friday night, I mean, not Friday night, because I still need to print out the exams. But there's plenty of space. So even if people sign up and then don't show up, that's fine. But I do need people to actually sign up to let me know how many exams to print. I can have extra exams, that's fine. I can throw them out. But if I run late, then it's going to come out of the student's time. Yes.
In terms of your study, are the examples in the OneNote, like at the end of the lectures, are